present today our course of optical communications. I'm Dr. Aziati Husna Awang from UiTM Shah Alam. This is an objective-based education course. Therefore, we will highlight the course outcomes once you completed it. There are actually 3 course outcomes for this course, and students are expected to be able to distinguish between different fiber types in terms of their attenuation, dispersion, and interconnection techniques. Students are also should be able to evaluate the parameter used in the optical sources, optical detectors, in the multiplexing technique, which is multiple wavelength division multiplexing techniques. And finally, when provided with some technical limitations, students should be able to design the solution for the optical communication system. So for this course, there will be 3 kind of assessment that will be done throughout the course. There will be 2 tests, consist of 30% of the final mark, 1 assignments carrying 30% of the final mark, and the final examination, or what we call final test, will carry 40% of the marks. So these are the overview of the optical fiber. So fiber optic is actually a medium for carrying information from one point to another, right? So this is the fiber optic part. Okay, so the basic fiber optic system consists of transmitter. The transmitter is actually a converter for electric signal to optical signal, so that it will be carried through the fiber optic. And we also have at the other end is what we call as a receiver. This receiver will convert back the optical signal to the electrical signals, so that it will be deciphered into feasible information. Okay, so the transmitter that being used normally is LEDs and also laser diodes, and the receiver that always be used is photodiodes. This rapidly expanding information system requires ultra high capacity optical transmission system. That's why fiber optic comes into pictures. Previously, copper were used for the transmission medium for data communication. However, the limitation in the bandwidth and also the capacity open up space for fiber optic communications to take place into this technology. So the multiplexing technique used in optical fiber communication is wavelength division multiplexing. So some regenerative amplification also used to effectively employed in the optical transmission networks. So let us see some of the advantages that fiber optic have over copper system. Fiber optic can be employed for long distance transmission. It is also would be able to carry high capacity data up to 10 terahertz in terms of bandwidth. Its small size and low weight has become useful in the network systems. Okay, and it has also less signal degradation and also less loss. The cabling system that been employed in the fiber optic has ensured electrical interference immunity. With this, no electricity passing through the optical fibers, we can say that optical fibers have an enhanced safety. This also will increase its security, signal security. That's why we can easily decipher back all the signals at the end, at the receiver part. Okay, so electromagnetic, here we can see the electromagnetic spectrum that we have in this world. Okay, so optical fiber is actually in between the infrared and also ultraviolet. It falls between in the infrared region, and also some will be in the visible light region. Okay. So normally a typical human eye will respond to the wavelength from about 390 nanometer to 700 nanometer, and optical fibers ranges from 770 nanometer to 2.55 micrometer. So these are the range for wavelength for visible, not only for visible light, for ultraviolet and infrared also. The visible wavelength is in the region of, as mentioned before, the ultraviolet is the region with wavelength shorter than 380 nanometer, and the infrared is for the wavelength which is longer than 780 nanometer. So our wavelength, our fiber optic wavelength basically falls into this range. So how actually, so what are the frequency range that normally used in the fiber optic? The full spectrum fiber extended from 120 nanometer to 1250 nanometer to 1600 nanometer. However, normally used wavelength is in between 1350 nanometer to 1450 nanometer. Why? This is because these are the conventional zero water peak fiber whereby the loss is minimal in this region. So normally we will use this frequency band. This is the most optimum wavelength to be used for the source in conjunction with the fibers, so that we have a minimal loss. So we'll see here, there's actually a few band that that normally used with fiber optic communications: original band, extended band, short band, conventional band, long band, ultra long band, O band, E band, S band, C band, L band, and UL band. Okay, U band. So these are the spectrum, the range of spectrum that we have for all the bands. Okay, so let us walk through a bit on the what we call history of fiber optics. Okay, so fiber optic, which is the science of light transmission over a fine glass of plastic fibers, continues to be used in more and more applications due to its advantages over copper product. So here let us go through the path where light has become the best option for data transmission. We can see that in 1980s, two physicians demonstrated the ability to direct light along curved water. This technology has been used in water fountain displays. Okay, in 1854, John Tyndall discovered that light can be conducted through a curved stream of water. So this is the experiment. So this is the experiment that always been unified with John Tyndall. Okay, the earliest demonstration of basic principle of light propagation in a fiber optic. This is what we call total internal reflections of light shown exists in the stream of water. The sun rays could be detected in the in the basin. So how does the sun rays could be detected in the in the basin? Is from the water flowing out from the basin to the green basin here. Okay. So in 1880, another experiment called light pipes have been shown by William Wheeler. So this is also another proof that lights can be propagated through a medium. Okay. So in 1930, the first image, which is the first data, successfully moved from a curved optical fiber during experiment by a German medical called Heinrich Lamm. Okay. And in 1960, American physicists developed the first laser. Okay. These are the patterns from the William Wheeler in 1881, shown an experiment of a pipes carrying lights from one end to another end. This is our laser man, Theodore H. Maiman, with his invention of ruby laser. So in 1966, a scientist called Charles Cow discovered a quartz glass and invented fiber optics. So this is the man of a fiber optic ourselves. Okay. This is Charles Cow in his chamber doing experiments for the first fiber optics. Let us look at why we need fiber optic in our optical communication system. So there is a need to have higher bandwidth with higher capacity. So it is predicted from 2001 that we gonna needed about 10 terabit per second for our future communications. So we need high capacity systems to be able to have a high data rate communications. So it is expected that hyperscale taking the lead in the new technology adoptions from 2018 onwards. Previously, these data communications are monopolized by enterprise and telecom, but in the future there will be hyperscale taking the lead. Okay, so this is another block diagram for fiber optic communication. Okay, so the transmitter block uses an electrical interface, either video, audio, data, or other forms of electrical input to encode the user's information through modulation. Three forms of modulation are typically used: AM modulation, FM, or digital modulation. An electrical output of the modulator is usually transformed into light either by means of LED or LD. Okay, so these are the transmitter. A modulator that we call to modulate the digital signals, pulses, and transform it into light. Okay, and then the fiber optic cable, which is the light pipe, carries data from one point to another. Okay, the receiver decodes the light signal back into electrical signals. Typically, light detectors such as PIN photodetectors or avalanche photodetectors has been used. These detectors are made from silicon or indium gallium arsenide or germanium, and these detectors detected and amplify the signal, electrical signal, and send it through a data encoder or demodulator that converts the electric signal back into video, audio, data, or other form of user input. Okay, let us have a look at the fiber that normally used in fiber optic communications, the general fiber optic cable. So what we have here is a core, okay, normally it's either ultra pure glass or plastic, and then we have a cladding. Normally this cladding is the same as core, material is the same as core but different refractive index, and we also have a protective jacket, okay, to encapsulate the cladding and also core. So our information which confined in core is well protected by the cladding and also protective jacket. This has ensured the safety of our information. Let us have a look at light transmitted through optical fiber. Okay, the light transmitted through the optical fiber uses a light principle called total internal reflection. This can be ensured by using a medium 1 of higher refractive index than a medium 2. Okay, when medium 1 having higher refractive index than medium 2, total internal reflection can be ensured to happen. If the light incident at the boundaries is much angle of light incident at the boundaries is greater than the critical angle for the N1 and also N2. We will go through the total internal reflection in detail in the future chapter. Okay, so how do we calculate the power level? The optical power is a measure of rate at which electromagnetic waves transfer light energy. Okay, to ensure the wave incident on detector has sufficient strength to be clearly detected and also correctly recognized. So, the power level is actually a rate of change of energy flow from one point to another special point at a given special time. Okay, so this optical power can also be stated in terms of decibel relative to the power level, such as dB millimeter or dB micrometer. The decibel is a convenient measure of power level in communication system. Okay, so if you want to calculate the decibel, you can use this equation. Okay. So if we consider three blocks that represent a coupler from a light source to a fiber, then the fiber itself and a connector. So we have 4 fibers point here. Okay. 1 fiber, 2 fiber, 3 fiber, and 4th fiber. Right. So the output power can be determined by multiplying the efficiencies of each block fiber. Okay. This is the equation that can be used okay. Just bear with me for a while. I'm actually zooming it out and in and out. Okay. Now let us continue with the expression in dB. This is how you write it in dB. Okay. So the nature of light, normally light can be described in 3 ways. We can either describe it in terms of rays, electromagnetic waves, or photons. Okay, in this course, we will treat light as rays. Okay, so when we treat light as rays, a few rays law that should be obeyed, where we can say that rays travel at velocity c in space, but we can calculate the velocity in other medium by using this equation. Okay, velocity is equals to the velocity of light in space divided by the refractive index of the medium. Factor is in refractive index. Okay, so the ray law also said that rays travel in straight path unless deflected by some changes in the medium. The fourth law said that at a plane boundary between two media, a ray is reflected at an angle equal to the plane incident. So, for a reflection to occur, the total incident angle is equal to the total reflected angle. If any power crosses the boundary, the transmitted ray direction is given by Snell's law. Okay. So refer to the electromagnetic spectrum. The term optic is actually referred to frequencies in the infrared, visible and ultraviolet portions of the spectrums. Those three spectrums are referred to as optic spectrum. So light waves have much higher frequency than radio waves, but they both obey the same laws and share many characteristics. In free space, electromagnetic waves travel at speed of light. See, so thus optics rays. In solid media, wave velocity is deferred. The value depends on the material and on the geometry of any wave guiding structure that is present. The wavelength of a light is actually equals to the velocity divided to the frequency. Photons, in 1905, Albert Einstein and Max Planck showed that when light is emitted or absorbed, it behaves like an electromagnetic wave and sometimes behaves as though it were made up of a very small particles called photons. This theory is known as Planck's law. Okay? Planck's law stated that when visible light or high-frequency electromagnetic radiation illuminates a metallic surface, electrons are emitted. Okay, so therefore Planck's law can be expressed mathematically as energy emitted, WP, is equals to the Planck constant H times the frequency of the electromagnetic spectrum. Okay, thank you for the attention.